Hello, in this lesson we will study the sum and difference formulas for trigonometric functions. These formulas allow us to evaluate exact values, simplify expressions, verify identities, and solve more advanced trigonometric problems. Throughout this lesson, you'll see how these formulas help us work with angles that are not found directly on the unit circle. Let's get started. In this section, our goal is to learn how to use sum and difference formulas to evaluate trigonometric functions, verify identities, and solve trigonometric problems. Rather than memorizing isolated answers, we'll learn how to break complicated angles into simpler angles whose trigonometric values we already know. By the end of the lesson, you should feel comfortable applying these formulas in a variety of situations. This slide summarizes the 6 sum and difference formulas that we will use throughout the lesson. Notice that there are formulas for sine, cosine, and tangent. One common mistake students make is confusing the signs in the cosine formulas. A helpful memory aid is that cosine changes signs between the sum and difference formulas, while sine keeps the same pattern and only changes the sign between the two middle terms. You do not need to memorize every formula immediately, but you should become familiar with their structure and know when each formula is appropriate. As we work through these examples, you'll see these formulas in action. In this example, we want to find the exact value of sine of pi over 12. Notice that pi over 12 is not one of the standard unit circle angles. Because of that, we rewrite it as the difference of two angles whose values we do know. We write pi over 12 as pi over 3 minus pi over 4. Now we can apply the sine difference formula. At this point, we substitute the exact unit circle values for sine and cosine of pi over 3 and pi over 4. After multiplying and simplifying, we obtain the exact value of square root of 6 minus square root of 2 over 4. Notice that we leave the answer in exact radical form rather than converting to a decimal approximation. This example illustrates one of the most important uses of sum and difference formulas, finding exact values for angles that are not immediately available from the unit circle. In this problem, we are given partial information about two angles and asked to find the exact value of sine of the sum of those angles. Before we can use the sum formula, we need all 4 trigonometric values involved. The given values allow us to construct right triangles. For angle U, we know the sine value, so we can determine the missing side using the Pythagorean theorem and then find cosine U. For angle V, we know the cosine value, so again we use the right triangle to find the missing side. A very important step here is determining the correct sign. Because the angle V lies in the second quadrant, sine must be positive while cosine is negative. Students often forget to use the quadrant information and end up with the wrong sign. Once we have all the necessary values, we substitute into the formula for sine of U plus V and simplify. The final answer is negative 33 over 65. Always pay close attention to the quadrant information whenever inverse trigonometric functions or triangle methods are involved. This example shows how some formulas can be used together with inverse trigonometric functions. We want to rewrite the expression as an algebraic expression involving x. The key idea is to let one angle be arctangent of 1 and the other angle be arccosine of x. Once we identify those angles, we can draw right triangles that match the given information. For the arctangent angle, tangent equals 1 over 1, giving us 45-degree reference triangle. For the arccosine, cosine equals x over 1, allowing us to determine the remaining side using the Pythagorean theorem. Drawing these triangles lets us find all the sine and cosine values needed for the cosine sum formula. After substitution and simplification, we obtain the final algebraic expression. This example demonstrates an important strategy in trigonometry. When inverse trig functions appear, drawing a triangle often makes the problem much easier. In this final example, we verify a well-known cofunction identity. Rather than assuming the identity is true, we prove it using a difference formula. We begin with the left-hand side and apply the cosine difference formula. Next, we substitute the known values of cosine pi over 2 and sine pi over 2. Since cosine pi over 2 equals 0 and sine pi over 2 equals 1, the expression simplifies immediately to sine of x. Because the left-hand side simplifies exactly to the right-hand side, the identity is verified. This example highlights another important use of sum and difference formulas, proving trigonometric identities. Many identities that appear complicated at first become straightforward once an appropriate formula is applied. In closing, in this lesson we learned the sum and difference formulas for sine, cosine, and tangent. We use them to evaluate exact trigonometric values, solve problems involving inverse trigonometric functions, rewrite expressions, and verify identities. As you continue solving trigonometry, these formulas will become essential tools for simplifying complex expressions and solving more advanced problems. Practice applying them and pay special attention to signs and quadrant information, since those are the most common sources of mistakes.